welcome everybody to a new season of our webinar cycle, Data Science and Statistics. It is our great pleasure to see you joining so many. And today we have the honor and the pleasure of welcoming Trevor Asti from Stanford University. Of course, Trevor is someone who does not need an introduction, but let me just say a few words. He's, as everybody knows, Professor of Statistics at Stanford University, where he's known for his research in applied statistics, statistical modeling, statistical learning, bioinformatics, machine learning, topics on which he has published 7 books and over 200 research articles, among which the so well-known Elements of Statistical Learning and Elements of Statistical Learning with R. Prior to Stanford, Asti has worked at Bell Laboratories for 9 years, where he has contributed for statistical modeling with R. Trevor is recipient of several, many awards, including Rhodes University Distinguished Alumni Award, Honorary Doctorate from Milfem University in Germany, Sigillum Magnum from University of Bologna in Italy, Senior Breiman Award from the American Statistical Association, is Honorary Doctor of Mathematics from the University of Waterloo, and Trevor is elected member of the United States National Academy of Science, as well as elected to the Royal Netherlands Academy of Arts and Science. Trevor has worked recently in sparse models for statistical learning, and this is exactly the topic of his talk today. Trevor, thank you so much for accepting our invitation. It's really an honor and a privilege, and the floor is yours.
Thank you very much, Paula, and good morning, everyone. Well, it's morning here, and good evening there. It's a pleasure to speak with you today. I should just say that I've known Paula for a very long time, and I've also known Portugal for a long time, and I've been to Portugal a number of times, and I've always enjoyed it. And my family's had vacations there, and it's just a lovely country, and you're all lucky to live in such a nice place. So I'm going to share my screen. And so here we go. So this is a talk. This is Sequoia Hall, which is where my home department is at Stanford. And okay. No. Okay. So so this talk is based on material that's in a book that I published with Rob Tibshirani and Martin Wainwright some years ago, which is the same name as the talk, and it's also a culmination of collaboration with many co-authors and friends and colleagues. There's Brad Efron and Jerome Friedman, and then a lot of graduate students that have come through Stanford and worked on these projects. I won't list all their names, but some of the names will come up as we go through the material. So the talk is about linear models for wide data. Okay. So what we mean by wide data is that you often have many more features than samples. And in this regime, the linear model has regained favor as a tool of choice. So in its simplest level, it means we model the regression function as a linear function of the features. Okay. And this is even with in this modern world where we have some magnificent tools, this linear model still plays a prominent role. So I list some of the projects here of the types of problems where this might apply. So in document classification, we have feature representations for documents. And so in the original case, we'd use something called a bag of words model, where you record the presence of each word in a particular language in the document to create a featurization. You can also look for the occurrence of so-called bigrams and trigrams. Bigrams are two words together, and of course that increases the number a lot. And there's documents all over the place on the web. Of course, somebody needs probably to mute. Yeah, and of course today these problems have come back in the with great prominence with large language models and transformers. We get featureizations for many types of sequences, including documents. In genomics, we have gene expression. You can have 20,000 genes are measured for maybe 300 subjects. And then one of the examples we're going to talk about today is in genome-wide association studies, where you can have measurements on up to, and maybe more, 2 million SNPs measured for 500,000 subjects. So big data sets, but in each case, the number of features is more than the number of observations. And web pages also fall into this category. So in examples like these, we tend to still use linear models. For example, linear regression, logistic regression, the Cox model. And since P is much bigger than N, we cannot fit these models using standard approaches. So what we use is what's known as regularization. So some common approaches to regularization, right? So this at the base level for squared error loss is the problem we want to solve. And so it's a very standard problem, but we're in this regime where P is potentially much bigger than N. So forward stepwise, what it does is it regularizes by only including a certain number of features in the model. And it does that by adding variables one at a time and in a sequence, and stopping when overfitting is detected. And amongst methods that find subsets of variables, forward stepwise is the most feasible when you've got a very wide data set. So it's a relatively easy problem to solve. You go, it's a greedy algorithm. Given the set that you have already, identify the next feature that best improves the fit of the model. And so there's efficient algorithms for doing that. Ridge regression is very old. It just recently had its 50th anniversary, 50-year anniversary. And it fits a model subject to the constraint that the sum of squares of the coefficients is bounded. So unlike forward stepwise, ridge regression always keeps all the variables in the model, but it controls the overfitting and in fact allows the fitting in the first place by shrinking the coefficients towards zero. And that controls the variance. And then in 1996, my colleague Rob Tibshirani invented lasso regression, and it fits a model subject to an L1 constraint as opposed to an L2 constraint. So ridge regression was an L2 constraint. Lasso uses an L1 constraint. So it constrains the sum of absolute values of the coefficients. And lasso, in doing so, does variable selection and shrinkage, while ridge only shrinks. And this cartoon illustrates what's the main difference between ridge and lasso. So these contours are the contours of the loss function in a simple two-dimensional example. This orange diamond is a constraint region for lasso, and this is a constraint region for ridge. And the whole point here is that for lasso, you often touch the constraint region on the corners, and that means some variables are set to zero. In this case, variable beta 1 would be 0, and beta 2 would be non-zero. So this is a very highly cited piece of work. As of the end of September, there have been over 55,000 citations according to Google Scholar for the lasso paper. What we show here is a picture of the ridge, what we call the ridge path and the lasso path. And so what we're doing here is we're showing, as we relax the penalty in both cases, on the left for ridge, how do the coefficients grow as the penalty is relaxed? And what we see is that for ridge, all the coefficients immediately become non-zero, and they grow in a smooth fashion. And eventually, this is a problem where the number of features is actually less than the number of samples, so we can fit the unrestricted least squares fit. So at the end of the path, it's just the least squares fit, and it shows how each coefficient changes as we relax the penalty. And this is the same thing for lasso. And what you notice is for lasso is as we relax the penalty, initially only one coefficient is non-zero, and then a bit later another one is non-zero, and then another one, and they move towards the same least squares fit. The other difference that we see here, and it's indicated in this picture, and this will come up in a moment again, is that the lasso coefficient profile is piecewise linear. And that's a consequence of using squared error loss and the L1 penalty for regularization. So L1 regularization has been around for quite a while. So it came up in the context of soft thresholding for wavelets in the early work of Donahoe and Johnston in 1994. And shortly after, Tibshirani then introduced the lasso for regression in 1995. So with wavelets, you have an orthonormal basis. Things are somewhat simpler, whereas for regression and general regression problems, the features aren't independent and you've got correlations and so on. There was a related idea called basis pursuit. It came out by students of Donahoe. And then these ideas took on really quickly and were extended to many linear model settings, such as survival models, logistic regression, and so on. It also inspired a new field called compressed sensing, which is relatively more recent. And so there's been a lot of offshoots from the lasso idea. So it's a great idea, the lasso, and like all great ideas, they're only going to catch on if you've got efficient algorithms for implementing them. Originally, the lasso was implemented just using convex optimization techniques. It's a quadratic program, and so the original implementations just used standard techniques in convex optimization. So the first thing is, it's convenient to change instead of using the bound constraint, which is a nice way of stating the problem, to convert it into the Lagrangian form. And so what we do is we add a Lagrange multiplier with the L1 constraint. And so this is the problem that computationally is a convenient one for solving, and they're equivalent. So that's for squared error loss. For linear logistic regression, you've got a similar model. Here, instead of modeling the response as a linear function, you model the logit of the probability of a 1 versus a 0 for two-class logistic regression as a linear model. And then the optimization problem involves a negative log likelihood, which you want to minimize, again, with an L1 Lagrangian term to penalize the L1 norm. And so in these forms, the idea is you'd like to solve the problem for a given value of lambda. Lambda imposes the penalty on the L1 norm. The bigger lambda, the more you punish for a large L1 norm, it's going to cause the coefficients to shrink towards 0 and set some of them to 0. And what you really would like to do is get a solution path for many values of lambda. And the reason is because we need to select lambda. And one of the tools that we use, in fact, the main tool we use for selecting lambda is known as cross-validation. And so, as you probably all know, the idea is you divide the data into k folds, maybe k is 10, and then on 9/10 of the folds, you fit the lasso for a number of values of lambda. We usually use 100, and here we're showing the lambdas on the log scale. And then you make predictions on the 10% that you left out, and you average your prediction errors. And you do this 10 times, because each time 9/10 is a training set, 1/10 a test set, and you average the errors, and you get some crude standard errors, and you get this, what's known as a cross-validation curve as a function of lambda. And so this is like test error. And what we see here is that the test error at the far right here is very high. That's because we've shrunk everything to 0. On the far left, it's higher too, because we're overfitting. And hopefully somewhere in between, there's a sweet spot where you optimize in the bias variance trade-off, and that's how we select lambda. And this is the minimum value over here. And often we move a bit to the right, more conservative, and we move within one standard error of the minimum. And so that's why 2 vertical lines are here. So the point here is that when we have models like this, they're easy to specify, but there's an unknown parameter lambda, and we need some guidance to select lambda. Cross-validation is the tool we're going to use. And for cross-validation, you need to fit the model many times for many different values of lambda in order to do this. So you need fast algorithms for doing this. Okay. So in 2002, Brad Efron, who's a wonderful colleague at Stanford, proposed a technique called least angle regression, and we joined him and wrote the paper on this. And what it is, it's a very fast algorithm for fitting the lasso for all values of lambda simultaneously. And it actually used the fact, which we showed you earlier, that the coefficient profile for the lasso is piecewise linear. So you can imagine, if you know it's going to be piecewise linear, and you can prove it's piecewise linear, then you should be able to get an efficient algorithm for figuring out what each of those pieces look like. And it turns out you can. And it turns out that for squared error loss, you can fit that whole lasso path with the same cost as a single least squares fit on all the data, up to a constant. And so here's the picture. Again, there's the criterion. Here's the picture. And here we've actually drawn vertical lines at the so-called knots. And the knots are the places where the piecewise linearity changes. And you can see it changes when a new variable comes into the model. So at this, we've got 2 variables in the model. As we change lambda, I'm showing you the relative L1 norm. And when a new variable comes in, you see all the slopes of piecewise linears change, and that's when they change. So in order to do this, you need to be able to detect when the next variable is going to come in, and you need to be able to update the slopes. And you can do that, and we have a package in R called LARS that does that. So that was a big breakthrough, and it meant now we could, and it's called the homotopy path for the lasso with squared error loss. And so, you know, it was a game changer, basically, because you could do this very efficiently. And so after that paper, there was a lot of work by myself and others to come up with similar algorithms for all the other lasso problems, right? And so, and we were able, there was a fair amount of success, right? We were able to do it for support vector machines, for the cost parameter, for the elastic net, we were able to do it for quantile regression, For logistic regression and GLMs, we had to use more approximate algorithms, and because the solution profiles weren't piecewise linear. And so that kind of slowed things down a little bit. And basically, after a number of years of work, these directions kind of ground to a halt because there were a lot of problems that we couldn't find these paths very efficiently. And so the algorithms now were much slower. Okay. So we needed a better idea. And this led to the algorithms I'm going to talk about today, and some of you may have seen already, and are encapsulated in our R package called GLMNet, or GLMNet. And what it does is it uses a very old idea for fitting these paths called coordinate descent. And I've listed all the members of the team of GLMNet, and it's a growing team. But initially it was Jerry Friedman, myself, and Rob Tupshirani. And then a short while after, my colleague Balasubramaniam Narasimhan joined. And then a successive group of students have helped add to the package and improve it. And so they listed here as well. And James Young is currently a PhD student of mine. And I should also point out there's a website, glmnet.stanford.edu, where it's a good place to go, and you can read documents about the algorithm, all the help files. There's lots of information now on this procedure. Okay, so what's the idea? The idea is to solve the lasso problem by coordinate descent. So what that means is, for any given value of lambda, right, you're going to optimize each parameter separately, holding all the others fixed. And when you do that, the updates are trivial, and I'll show you the updates. And then you have to cycle around and around until the coefficients stabilize. Now, this might sound like a somewhat naive algorithm, but it turns out it works really well. So what we do is we do this on a grid of lambda values from lambda max down to lambda min. And lambda max is a number that you can determine, and it's the smallest value of lambda for which all the coefficients in the model are still 0. Right? You imagine if you make lambda really big, all the coefficients are going to be 0 because you're going to give a huge penalty. You're going to punish any L1 norm. Well, it turns out you can find out where that lambda max is. And then we make a grid from lambda max down to lambda min, which is some small value slightly bigger than 0. And then there's two other important terms here. One is warm starts and one's active set methods. The warm starts are important. If you think about it, we start off where all the coefficients are 0. And then, so we know the solution there at lambda max. Then the next lambda is slightly smaller than lambda max. And the solution is going to have only a few coefficients that are going to be non-zero. And so this coordinate descent doesn't have many things that it needs to update. Most of the coefficients are going to be 0. And you get really good warm starts for the coefficients from the previous solution. Okay. Active set method says, even though you may have thousands of variables, what you first do is you have a very good idea which ones are going to be non-zero, and you first get a solution for them, and then you check to see if it's a solution for everyone, and the check is easy. So these are some of the reasons why coordinate descent is very attractive. But it mainly also means we can use a variety of loss functions and additive penalties. So coordinate descent achieves dramatic speedups over all competitors by factors of 10, 100 or more. And here's an example. You've got a documents database with 11,000 observations, 778,000 features. So this is a massive data set. The so-called X matrix is sparse, because this is bag of words and bags of bigrams and trigrams and so on. And we fit the whole lasso path with 100 values of lambda across the entire range using lasso logistic regression. And it takes 5 seconds to do on this computer that I'm using today for the presentation, which is extremely fast. So here's a solution path. And what I'm showing you here is that because of the way we fit it, we fit on a grid of values of lambda. And so we don't get the fit everywhere, but we get it on a fine enough grid that's sufficient. So in R, just to give you some of the idea of some of the features of this GlimNet package, we can fit for a variety of different GLMs, all the GLM families, and using the so-called elastic net family of penalties, which I'll tell you a bit about in a moment. So these models include the well-known GLMs and any GLM, multinomial, that's multi-class logistic regression, the Cox model, and also a multitask group linear model. The elastic net penalty includes ridge regression, lasso, and hybrids in between. We can handle a large number of variables. It does cross-validation for all the models. We can allow for sparse matrix formats for X and hence deal with massive problems. For example, the problem I just told you. And as of last year, the main computations in GlimNet are done in C++. In the original implementation, all the main computations were done in Fortran, written by Jerome Friedman. And last year, this graduate student of mine, very talented, translated all these procedures into C++, and that's led to speed ups, partly because of the not needing to copy big matrices, but it's made a difference. And so the package continues to grow. There's nice things you can do that are enabled by coordinate descent. You can provide lower and upper bounds for each coefficient. So for example, there's some scenarios where we want to fit a lasso, but we want all the coefficients to be positive. Well, it's easy to do for coordinate descent because we optimize in each coefficient one at a time. And so it's easy to set such bounds. There's something called a relaxed fit option, which I'll tell you later. And there's lots of other useful bells and whistles, which people who are used to working with GLMs like and need these things, such as offsets. Offsets are where you have part of the fit which you know already and you just want to include in the linear predictor. Penalty strengths. Sometimes you want to fit a lasso model, but some variables you want to penalize more than others, and some variables you don't want to penalize at all. And so we can use something called penalty strengths to do that. And then the obvious things like observation weights, intercept options, and so on, these are all accommodated. We're currently working on GlimNet Pi with a colleague, Jonathan Taylor, and Naris and myself. And so this is a Python package that's going to interface to all the same C++ code. And it's nearly finished, and it'll be announced fairly soon. Well, I guess I'm announcing it, but it'll be available fairly soon. So this GlimNet package has been it's been going for a number of years now, over 12 or more years, but it keeps on growing. And myself and my colleagues put a lot of effort into it. It's used a lot, and it's just one of these pieces of softwares. I think it's going to be constantly being developed and improved. Okay, so I'm going to tell you a little bit about more about coordinate descent and why it's so attractive in this context. So let's look back at our simple least squares problem and the lasso problem, and I've written out the criterion again. And let's just, for this demonstration, assume that we have that the response and the predictors are all standardized to have mean 0 and variance 1. Something we typically do with lasso anyway, because when you treat all the coefficients as equals in a penalty, it's it usually makes sense to have the variables or features on the same scale. Otherwise, the penalty would not make sense. So here's the idea, coordinate descent. So we're going to cycle over each of the features, 1 to p. And for each feature, we're going to compute the partial residuals. So that means we're going to subtract from y the fit using all the other features, all the other coefficients except the jth one, right? So in this criterion here, I'm going to subtract from this sum here, I'm going to take the partial sum involving all the variables except the jth one, subtracted from y to make that residual, okay? So now I've just got a single variable problem involving beta j, right? And then it turns out, and then for that variable, the only part of the penalty that applies is the absolute value penalty on beta j, okay? So then it turns out to compute the solution for that beta j, holding all the others fixed, you do two things. The first is you compute this simple least squares coefficient for that partial residual on the jth predictor. And because of the standardization we've done, that least squares coefficient is just given by this quantity over here, which is essentially an inner product with a residual. But that's not quite the solution yet. Then we have to apply soft thresholding, which is an idea that came up with the wavelet shrinkage. And what that means is you subtract from this beta star lambda. So yeah, this picture shows it. You subtract lambda. If it's bigger than 0, that's the value. If it goes below 0, you set it to 0. And likewise, if it's negative, you add lambda and set it to, so it's called soft thresholding. So these two simple operations, an inner product, soft thresholding, gives you that solution for that particular coefficient. And then you go on to the next one, and you go right through from j through 1 to p, and then you go back to the beginning and you keep on cycling. That will converge to the solution to this problem for this value of lambda. While we're here, you can see that we can efficiently deal with data that are sparse. So if you have an X matrix that's sparse, that means most of the entries in any row or column are 0. Okay, and the matrix is typically will be stored in what's known as sparse matrix format. So very easy in that case to compute. This is the main work for each coefficient, to compute this inner product, because you're going to just be summing over the entries in that X that are non-zero. So you can easily exploit sparsity. So elastic net is a generalization of lasso, which was introduced by one of my former PhD students, Hui Zhou, who's now a professor at University of Minnesota. And it mixes lasso penalty with a squared error loss penalty. And for technical reasons, it does it in this form. And so you've got an additional tuning parameter alpha, which says how much lasso and how much ridge. Okay? And by default, if alpha is 1, it's a lasso problem. Alpha is 0, it's a ridge problem. And for alphas in between, it's something in between. It's called the elastic net. And it turns out the coordinate descent algorithms very similar to what it was for lasso. The soft thresholding operation is now slightly different, and it's got a bit of a lasso component, which is in the numerator, and a bit of a ridge component in the denominator. And here's the corresponding picture. So both for the whole elastic net family, this coordinate descent is fairly straightforward. Here's a picture I often show, which shows the difference between lasso. This is the beginning of a path for a genomics problem where we're doing a logistic regression. Here's pure lasso. Here's elastic net with alpha equal 0.4, and here's pure ridge. And what you see by, and these are all at comparable distances along the path. And what you see is for lasso, fewer variables have come in and are non-zero. For ElasticNet, more have come in, but they shrunk more. And for Ridge, everything's in, and they all shrunk heavily. Okay. And the reason we use ElasticNet is when you've got correlations amongst your variables, Lasso doesn't do very well. Right? If variables are extremely correlated, Lasso doesn't know how to choose between them. And what ElasticNet does, or tends to do, is bring in correlated variables in groups. And so that's why it was proposed in the first place. Okay, so I'm aware that time's marching relentlessly onwards, so I'll just quickly mention a few things here. There's been proposals related to these procedures. So there's methods for doing sparser than Lasso. This is one of my past students, Rahul Mazumdar. So we have work on that, and we have a package SparseNet. I was going to tell you about best subset selection, which in recent years had a breakthrough, and also due to my student Mazumdar, who's now a professor at MIT, using something called mixed integer programming, where you could fit best subset much more efficiently. Still quite slow, but much more efficiently. And this led to some work with myself and Rob Tibshirani and his son, Ryan Tibshirani, who's now a professor of statistics at Berkeley and a famous statistician in his own right. So this is a fun picture of Rob when he was much younger with a young Ryan as a young kid. And based on this, inspired by this breakthrough in best subset selection, which seemed to challenge the need for Lasso and quick ways of finding subset models in the first place, we did a study of a comparison of best subset selection forward stepwise or Lasso. Okay. And there's a paper published in Statistical Science in 2020. And our conclusions were that forward stepwise is very close to best subset, but much faster. In wide data settings and low signal to noise ratio, Lasso can beat best subset and forward stepwise in performance. And the one I'm going to tell you about in a moment, relaxed Lasso, was the overall winner, except in very high signal to noise ratio regime where best subset wins. And the relaxed Lasso is the fastest by far. What we mean by high signal to noise ratio, when you make simulations and when people make simulations to test procedures, they have to decide how much noise to put in the model, because you make everything up. You make the signal, you make the noise. And that decision, how much noise to put in is really important. And high signal to noise ratio means that there's lots of signal and very little noise. Right? So the problem's almost deterministic. So you've got to be aware when you make simulations. If you want to make simulations that sort of reflect real data and the way we see data in real problems in the world, it's important to be aware of how you've set the signal to noise ratio. I mean, my experience in practice is in real problems. Typically, the signal to noise ratio is much less than 1, which means there's more noise than there's signal. Like if you get a data set and you can get an R squared in test data, if you can get an R squared of 20%, that's often considered really good, right? And that means the signal to noise ratio is much less than 1. Anyway, that's a little bit of an aside. So we did a lot of simulations in this work, and here's one of them. The signal to noise ratio is 0.7, and what we're showing is expected prediction error, and this is indexed by subset size, but the methods we're comparing are best subset, forward stepwise, and Lasso, and you can see that best subset and forward stepwise are somewhat similar, but they bottom out at a relatively small subset and then start overfitting. And the true subset size here, was 5. So they actually pick on the right subset, but in terms of prediction error, the lasso ends up with a bigger subset, but does better in terms of prediction error. And this was something we saw over and over in these simulations. I can see I'm already butting up against my time constraints here. So I'll just tell you briefly about the relaxed lasso. The idea of the relaxed lasso is if you fit a lasso model, wherever you stop, you've shrunk some coefficients towards 0 and you've set many to 0. The idea of the relaxed lasso is that shrinkage is potentially cause some bias. So what you do, the idea is to identify the variables that are non-zero for the lasso and somehow now debias them. And the way we do it here is we actually take what's known as the active set, and then we refit the model just with those variables, but unconstrained. Okay. So that's what we call the relaxed lasso. So what we'll do is we'll take the solutions along the lasso path that we found using our coordinate descent algorithm, and for each of those active sets, we'll fit the model unconstrained. Okay. And so that's another sequence of fits, and it's fast. We use our same algorithm for doing it. And then what we actually do now is we make another family, which is a mixture between the regular lasso and this what we call least squares lasso, and where we mix with the parameter gamma, so we can get relaxed models in between lasso and the unconstrained one. So that's what we call relaxed lasso. Because having ones in between comes free of charge. You just fit these two paths and you can get all the paths in between. So on that same picture that I showed you before, this was the performance of just plain lasso, and this is the relaxed lasso with two different values of that gamma parameter. And you can see it does slightly better, and it gets closer to the true active set, which was 5 here in this case. Okay, and so the GlimNet package that I told about also now has the relaxed lasso, so you can do that as well for all the families, GLMs, and so on. Okay. Okay, so I am going to, I can see the time is up. So I'm going to stop very soon here. I'm just going to jump ahead. I'm skipping the screening rules. I just want to tell you that one of the projects that we've been working on and continue to work on is using these lasso models to fit what's known as polygenic risk scores in big wide data sets in so-called genome-wide association studies. Okay, and we've been fitting models on the UK biobank data where, for example, the one subset we have is we have 805,000 SNPs and 330,000 individuals, and we fit these lasso paths on big data sets like that, and we have a variant of the package called SNPnet. I can see I don't want to wade into this because it will take too long. So actually, I think at this point, since I've used up 45 minutes, what I'd rather do is pause here, and we'll stop here and open up for questions from the audience. Paula?
Thank you very much, Trevor, for this very clear and really very interesting talk. And now the floor is open for questions or comments. Please, anyone, feel free.
I'm going to change a picture so there's a better picture to have here. Yeah, this one's maybe better.